will start on chapter 11. For chapter 11, I believe, again, it should be more than one video, and we will see how it's going to be. In chapter 11, we are talking about the rotational dynamics. Remember, in chapter 10, we introduced the rotational kinematics. Then we were able to describe the rotational motion. And today we will talk about like how these kinematics they're gonna change, or like how we the object is gonna gain, let's say, acceleration. Why is that? And we are going to introduce new quantities today. And by the end also we will talk about like static equilibrium and how these like objects they can attain that equilibrium. What are the conditions? The first quantity that we are going to introduce in this chapter, it is torque. And we will find out how we are going to calculate the torque, what is the relation between torque and angular acceleration, and then we are going to move to the static equilibrium conditions and find out what are the conditions needed for static equilibrium. We will talk about the center of mass and its relation to balance. We will talk about dynamic applications of torque. Then I have objects that they are in rotation. How can I find maybe their, let's say, angular acceleration, or find the linear acceleration of an object, or talking about calculating some of the forces in systems. And I will talk about a new quantity called angular momentum and how it is different from linear momentum. And then I will introduce the conservation of angular momentum. And finally, we will talk about the rotational work and power. And of course, during all of this, we will not forget about the vector nature of rotational motion. Now, in order for us to start a rotation, we should have a force. And I will say here that not only a force, but that force should be acting at a distance from what is called like axis of rotation. Now, the direction and placement of the force makes all the difference. Where the force is located, for like what's the magnitude of that force, and also in the same time, I will say how far it is from the axis of rotation. This is gonna make a very big difference. This is I will say just as if we are looking from the top on a door that it is opening. Try opening the door by pushing near the knob versus pushing near the hinges. Okay, and how this is gonna be like here, these three forces, which one is gonna be the best one that is, or I will say the most effective one in the rotation. Okay, just okay, I post these questions. Now, from experience, and everybody I think did this in a way or another way, we know that the same force will be much more effective in rotating when it is not too close to the axis. Okay, and we feel it. Okay, try this. Go to the door of your room and try to apply a force far from the axis of rotation or the hinge, and try another force very close. This is why we have long handle wrenches and why doorknobs are not next to hinges. And I remember maybe like I was looking maybe at this a set of like screwdrivers, and they have the same head, and then why they are like some of them are longer than others, and I have that question when I was maybe a kid, and looking at that and was asking why is that, or what's the reason for that. And this is the reason. When you have a long arm, you are going to get them more effective. Now, the quantity that we are defining, it is called torque, and it is, I will say, the rotating effect of a force. Not all the forces, they have torques. We can calculate torque as R times F. Tau, this is, and I use uppercase R. Oh, no, let's stick with this lowercase. All right, now the SI unit, based on this, of course, it is in newtons times meters. And we can see that the torque increases as the force increases and also as the distance increases. Okay, then here, which force will produce the most torque? Okay, now we might answer that question. And of course, A is not going to have any torque because it is going, like its line of action is going through the axis of rotation or through the hinge. This one also is very close. This one is the one that is going to get more torque. We can say here that torque is R times the force that is perpendicular. Then not all the force is going to participate in the calculation of torque. The perpendicular component of the force that is going to participate. And in general, okay, I like maybe to introduce this equation before we start, like it's gonna be later in this slides or PowerPoint, but I like to introduce it here. And just here I want to tell you that theta is the angle between F as a vector and R. It has nothing to do now with the x-axis. It has to do with the relative direction of F and R. Okay, using a wrench here, you are using a wrench to loosen a rusty nut, which arrangements will be more effective in loosening the nut. Of course, I will say this is the one because it is more arm, like it's just gonna have more torque. Also here, we are going to maybe talk about two forces produce the same torque. Does it follow that they have the same magnitude? Of course, no, because the torque depends on the force and also the distance. Now, torque here, I will say only the tangential component of the force causes torque. Which means here we are going to, find that this one here, which is, we call it F perpendicular, that is gonna cause the torque, because that one, the other component, it is along the, I would say along the arm of, along the axis of rotation, and it will not create any torque. And this leads now to the equation that I have introduced for you, which is tau equals RF sine theta. We can write this as all sine R sine theta times F. It doesn't, like either way is gonna work. You need to find the component of the force that is perpendicular to the lever arm. Okay, then we need to analyze the force here. This is gonna be F cosine, and that one is gonna be F sine. All right. Now also remember, we need to maybe find out if that torque is a vector quantity or is it a scalar quantity. It is a vector quantity, and the direction we are using for it, either the negative or the plus. We consider the counterclockwise to be positive, and we consider the clockwise to be negative. How we will be able to, determine the direction, I want to show you like a very straightforward, method. Where is the force? You're going to have a vector that is going to represent the direction of R, and it is from the axis of rotation out, like this. This is, I call it the direction of R. All right? Now, you're going to bring this to this, R to the force. And if you look at it, this one, it is giving us the rotation that is gonna be, this one is R to F1 is going to be the positive. And here I will say this is the one that is gonna be the negative. I don't know why these here are really switched. Okay, then if the torque causes a counterclockwise angular acceleration, it is positive. If it causes a clockwise angular acceleration, it is negative. This is how we represent the direction. Now, try using it. Okay, a 1.61 kilogram bowling trophy is held at arm's length, a distance 0.605 meter from the shoulder joint. What torque does the trophy exert about the shoulder if the arm is horizontal, or if it is at an angle 22.5 below the horizontal? Now, I did draw here, and of course that force is gonna make that rotation, which is negative. Remember the rule, and then the torque is gonna be negative. And here actually the sign is not very important because I have only one torque, then I am just comparing two torques. One of them when the arm is straight, and one of them is when the arm, it is an angle of 22.5 below the horizontal. Now, of course, but I want to maybe follow the rules for the calculation. Minus mgr sine 90, and that is going to give us negative 9.55 in Newton meters. When we, okay, because here sine 90 is 1. Whenever we are going to include the angle here, okay, I did that, and the angle that I'm gonna consider, you can consider the 22.5, but I like always to use the angle that it is truly there, and it's not gonna change anything in the numbers. mgr sine 67.5, which is 90 minus 22.5, and that is gonna give me minus 8.82 Newton meters. Then the torque is going to change based on the angle. The 90 is going to give you the maximum torque. Now, what is the relation between torque and angular acceleration? Okay, this is a Newton's second law, F equals ma. And then what I can do is here is I can multiply R on both sides. There is a missing R here. R times F equals MRA. Now, torque is RF, and this is going to be MR squared times alpha. Oh, I'm sorry. No, here, I'm sorry. No, okay. Let's repeat this here. This is F equals MA, and here this is alpha, not A. I thought this is A. This is alpha. Then I did use from the previous chapter, alpha times R is my A. And then I multiplied by R, Okay, then here, if you will multiply here by R and here by R, you're going to get RF, which is the torque, and here mr squared times alpha. This is the number that we are using for the moment of inertia or the rotational inertia. Then the net torque is going to equal I times alpha. And this is the alternative, or like this is a second statement of a Newton's second law, which applies to rotation. Now, also, we need to bring to your attention that there are, and again, analogies between the angular and the linear motions. The mass, it is related to inertia, and I, it is the rotational inertia. A, it is the acceleration, and alpha is the angular acceleration. Force, it is the cause of the change in the acceleration, and torque, it is the cause for changes in alpha. And finally, we can say here, this is sigma F equals ma, and this is sigma torque equals I alpha. And we are going to go, when we are going to talk about the dynamics more, you are going to have most of the time two objects in your system, two objects at least. One of them is doing linear motion. Then you are going to draw free body diagrams for that motion, and you are going to calculate, the acceleration. And here you have the, I will say, the rotational motion. And for example, you have a pulley, and then you are going to apply the rotational motion. Okay, and you will connect these two equations and get your unknowns calculated. Here I will say, when summing torques, watch your signs, because these are very important. If the torques are in the same direction, then the net torque is going to add. If it is in opposite directions, then you will have subtraction. And here I can say this is my R, and this is the torque that is, negative, and that one is going to be the positive. Okay, and when we are going to have like them equal in magnitude but opposite in direction, they're going to cancel each other. Now try using it. A person holds a ladder horizontally at its center, okay, and treating the ladder as a uniform rod of length 3.15 meters and mass 8.42 kilogram. Find the torque the person must exert on the ladder to give it angular acceleration of 0.302 radians per second squared. You need to go to your, for the table for the moments of inertia, and find out that whenever we are having an object that is a rod and we are rotating it about its center of mass, this is I for the rod that I'm going to use 1/12 ml squared. There is another one which is 1/3, and that 1/3 is going to be the one that is going to be used when you are rotating the objects, when you are rotating the, I would say, an object about one of the ends, and it is 1/3 ml squared. Okay, then you have to pay attention when you are pulling your I will say equations. Okay, a person again holds a ladder horizontally at its center. It's reading the ladder as a uniform rod of length 3.15 and meter and mass 8.42 kilogram. Find the torque of the person must exert on the ladder to give it angular acceleration 0.302 radians per second squared. I did draw the ladder here, and with alpha we're going to treat the ladder as a rod. Then I rod when it is rotating about its center of mass is going to be 1 over 12, 8.42 kilograms, 3.15 meters squared. And this is going to be 6.96 kilograms meters squared. And sigma tau, okay, this is in Newton's second law. That is going to be for rotational. And I times alpha is going to be 2.10 in Newton meter. The unit is wrong in the video, like it is a Newton per meter, but like, of course, it is not. It is like, you know, sometimes we make these mistakes, but just I want to pay your attention. Now, this is going to be your exit ticket for chapter 11 here. I want you to repeat this question, and you should calculate the torque, like repeat the same question here, but I want you to find the torque when the person is gonna try to rotate this object, which is the ladder, at its end instead of one of the ends, not at its center. Okay, then this example here, it is about rotating the ladder at its center. I want you to recalculate the torque needed, but when that person is attempting to rotate this object with the same alpha, okay, at one of the ends. Okay, this is your exit ticket for chapter 11. Now, we are going to go and talk about zero torque and static equilibrium. Then when I have static equilibrium, what are really the conditions for static equilibrium? Now you need to guarantee two things. The first one is at rest the object, neither rotating nor translating. And we will guarantee that the object is net force is 0. Then I will split this into sigma fx equals 0 and sigma fy equals 0. And the net torque acting on the object must be 0, which is sigma torque should equal 0. Now, this is really one of the examples from the textbook. And talking about the net torque here is 0 because it doesn't matter which axis we consider rotation to be around. We are free to choose the one that makes our calculation easiest. Then when you choose that axis of rotation, it is completely arbitrary, but one choice will make it like very difficult to solve the question, and another one is going to make it very easy for you to solve the question. And I will suggest usually to use that axis of rotation or like the calculation of torque about a point where we have more of the forces that they are unknown. Okay, then if you have a point where the forces are not known, choose this point for your axis of rotation in reference of calculation for torque. Now I have here a 0.122 kilogram remote control that is 23 centimeter long, rests on a table with a length L overhanging its edge. To operate, power button on this remote requires a force of 0.365. How far can the remote control extend beyond the edge of the table and still not tip over when you press the power button? And that the power button is 1.41 centimeters from the overhanging end of the remote. I did the draw, like imagining that this is my remote control. I assume always that my objects are uniform. What does that mean? This means that the weight is acting at the center of the object. And if I will consider that I will say, remote control to be rectangular shape, then this is how it's looking. And this one is going to be the X center of mass, and it is half of the length, 11.5 centimeters. The force that I'm going to apply is going to be here, and it has that distance, which is, we call it LP, and that LP is point, like I need to convert, of course, this in centimeters into meters, 0.0141. The mass of the remote control, it is 0.122 kilograms. Now, in order for, it's, of course, here, I will say it will, when it will flip, it will rotate about this point here, which is really the edge of the table. I can say that mg times, like that here is going to start, this one is going to try to rotate it this way, and that one is going to start try rotating this way. And then these two torques, they should balance. Then FB, the force applied, times L minus LB should equal mg X center of mass minus L. I have here FB. I have calculated here also the weight of the remote control, and then I did substitute my numbers, and then I found L equals 9.14 centimeters. There is a number that is not correct in the video, and also here the X center of mass. Okay, the X center of mass is going to be half, which means 11.5 centimeters. Okay, here also, this is another question where 1 kilogram ball is hung at the end of a rod that is 1 meter long. If the system balances at a point where on the rod 0.25 meters from the end holding the mass, what is the mass of the rod? Of course, we know that the weight is acting at 0.5, and when it is balancing at this is 0.25, then the other segment here is going to be 0.25. Again, the torques, this is negative, this is positive, they should balance. And then MB, the ball, times the weight of the ball, times 0.25 should equals MR times G times 0.25, which means the ball has the same mass as the rod, which is 1 kilogram. I think I'm gonna stop here.